name is Dana Golden. Today we're going to be finishing up the environmental data unit before we move on to geographic information systems. And we're going to start off by looking at the hedonic pricing model. So key components, you have a dependent variable that is the price of the good, which is either the property or product price. You have independent variables, which are structural attributes, which are characteristics of the good, size, age, and features of the good. You have locational attributes that are geographic location, proximity to amenities, environmental factors, and then you have a explanatory variable you really care about. All the others are controls, and that's the environmental contextual attributes, non-market factors like air quality and noise levels. When you're thinking about getting this data, make sure you have an accurate measurement of price and attributes. Do things like adjust for inflation, make sure everything is on the same scale, make sure you know when the transactions happen so you can make sure there's nothing funny, and make sure that there's a lot of variation, preferably in all the variables, but definitely in the price of the good, and in non-market factors that you're interested in, like air quality. And you obviously want a large enough sample size to capture heterogeneity, and you want a sample size that has differences in it. You don't want all the houses in one neighborhood. You want houses scattered around so you can run the regression. So here's the Hedonic regression. You have price equals beta 0 plus beta 1 plus beta 2. All these are attributes of the good. And then plus beta k. Let's say beta k is the air quality that we're interested in. So coefficients for each attribute xk represent marginal implicit prices. This is how much individuals value this. And the neat things about these is these are in dollars. So this is how much in dollars people value air quality. So it allows you to put a dollar value on an environmental factor. So the price of a house equals beta 0 plus beta 1 size plus beta 2 age plus beta 3 times proximity to park. Here we're seeing how valuable the park is, protecting nature and having a place where people can come together. So if you want to estimate this in R, first off you load the tidyverse library. If you're running this in R and you're like, oh, my code doesn't work, you need to install the library tidyverse. So install tidyverse and then just do library of tidyverse. Then you can create a tibble, which is just basically a data frame, but specific to tidyverse. And you put in each of the variables. C allows you to create a vector. So this is a vector of prices. This is a vector of sizes. This is a vector of ages. And this is a vector of product proximity. You can probably do it as a Boolean, but I think here they've done it as an integer. So then you fit the hedonic pricing model. You do model goes to, and now you'll have the model saved. Model goes to LM linear model. So this is a built-in function R. You don't have to import anything. Of price. You have this tilde, which means price is a function of size plus age plus park proximity. And then data, this argument is you write in data and then equals the name of your data set, in this case, data. So you've created the model, and then to estimate it, you just do summary of model. So LM fits a linear regression model, and summary provides the coefficient of model diagnostics. So another model we talked about earlier on in this class in non-market valuation is logistic regression. Logistic regression is a statistical model to predict the probability of a binary outcome. Success or failure, yes or no. Technically, you can also write what's called multinomial logistic regressions that do more than binary. Take a skip with binary. It's just, think of it as a 1 or a 0, and we're using it to estimate willingness to pay. Dependent variable is 1 or 0. So you've thrown off a lot of the assumptions of the statistical model of classical linear regression because you have a probability, so you shouldn't be greater than 0 because you or less than 0 or greater than 1 if you want to interpret it as a probability. So logistic regression, probability y equals 1 given x is equal to 1 over 1 plus e2, and then your formula with all the betas and all the x's. So betas are the parameters, and then y equals 1 given x is the probability. So notice this is 1, and this is 1, and this guy over here can never be negative. So it's 1 plus something positive, which is always going to be greater than 1. It's 1, so this will always be between 1 and 0, which is a nice little factor about this little guy, which is the logistic function, but also the softmax function, which has really nice economic characteristics. So this is used for credit scoring. It's a traditional application you'll see in other classes, but it's also used for resource valuation. It's probability of resource availability and also willingness to pay. Logistic regression for non-market valuation. Why use logistic regression? It predicts the probability that an individual accepts or rejects a bid for a non-market good, and it's useful at estimating willingness to pay. So y equals 1 accepts the bid, they are willing to pay. Y equals 0 rejects the bid. So this will allow you to get a function from bid amount to accepting, which allows you to get a coefficient on price, or coefficient on quantity, or coefficient on whatever you want for non-market valuation. And you can see how this is affected by demographics and attitudes and preferences. This can be used in evaluation of clean air, water quality, and park access. So here's a linear regression. It's a nice little linear regression, very few outliers, and it's just going up. It's straight line. And the logistic regression, there's a threshold value that you have a cutoff. Most people use 0.5 as a cutoff. There are other reasons why you'd want different cutoffs, but you have a threshold value, and then your data are all zeros or all ones, and anything beyond this line, you're going to say this is a 1. Everything before this, you'll say is a 0, and that is logistic regression. You have this sigmoid function here. Logistic regression for individual valuation. This is something someone could do as a research project, something like this. What is the probability that an individual is willing to pay X dollars for improved water quality in a local lake? So you have log probability y equals 1 over probability 1 minus 1 minus probability y equals 1 equals, and then you have beta 0 plus beta 1 bid plus beta 2 income plus beta 4 environmental concern. So y equals 1, respondent is willing to pay the bid amount, bid amount offered in the survey, income respondent is household income and level environmental concern. So maybe you can say more environmental concerned people are willing to pay, more likely willing to pay X dollars, and maybe the bid, as the bid goes up, that becomes more likely, and there's some bid after which basically everyone's willing to pay it. So mean willingness to pay can be derived as negative beta 0 plus beta 2 plus beta 4 over beta 1. So basically, you take these factors, you put them in here, and you get the mean, and you divide by the coefficient of the bid. So our code for non-market evaluation, again, we're just going to import tidyverse, create our tibble. In this case, take a look at what all these variables are. Accept, which are a dependent variable, 1 or 0, kind of a binary system there. Bids, different amounts they'd have to pay. Income is different amounts, so maybe richer people are willing to pay more. So we're trying to predict how likely you are willing to pay, and to back out mean willingness to pay, we're backing out how much the average person is willing to pay based on how likely different people are willing to accept different bids for the environmental resource. And you have some environmental concern. Maybe we ask them in the survey, because this is contingent valuation. This is discrete joint voice modeling. Similar to contingent valuation, but this is discrete joint modeling. We ask them, how concerned are you about the environment from 1 to 5? We fit the logistic regression model. So now, instead of using LM, we use GLM. Model goes to, this is that assignment operator in R, generalized linear model, except tilde. It means it's a function of bid plus income plus education plus environmental concern. Data equals data, and you have to specify a family of generalized linear model. You could, if you did normal, this would be a probit. In this case, it's a binomial, and then you put in summary of model, and you'll get the results. And then now if we want to calculate the mean willingness to pay, beta goes to the coefficient of the model. Average income goes to the mean of income. Average education goes to the mean of education. So this $sign allows you to get a variable from a data frame or tibble. So you get this data, and then $sign income is the income variable, the vector of incomes. Average environmental concern, you have that $sign there. And mean willingness to pay, we have the formula before where we have this beta 1. In this case, it says 2, but it's because of how our index is. It's not indexing from 0. And then you solve for this, and you now have the mean willingness to pay. So accept is a dependent variable whether or not they're willing to pay, whether or not they accept a bid. These are independent variables, and then GLM fits logistic regression. And mean willingness to pay is what we derived using the formula from before. So let's say you want to visualize the predicted probability of bid and acceptance. The probability that responds to accepted bid helps to identify trends in willingness to pay. You can use our friend ggplot. You'll need to install and then open the library of ggplot, but assume you've already done that. You use the data set, and then you provide the data variables you want plotted, bid, and then predicted probability, and then geometric line of blue. So now this will show you a line relating bids to probability. And then you just have axes and titles, and you create a plot. And ggplot is very useful for doing this kind of plotting. So another type of estimation we talked about in the class is production function estimation. So what's production function estimation? It's a method to estimate the relationship between inputs, labor, capital, environmental quality, and outputs, agricultural yield, and fishery production, or just production of the economy in general. We're going to talk about a very basic estimate of this. I have friends who work on this in IO, who maybe they're doing this very seriously. Maybe they're really seriously thinking about the endogeneity problem here. We're not going to do that. We're just going to pretend we're just going to run it as a very simple regression. Applications valuing water quality improvements in agricultural production and estimating the effect of air quality on labor productivity. General form Q equals F of K, L, and E plus epsilon. So our code for estimating a Cobbs-Douglas production function. You load up our old friend tidyverse, and you create your tibble. You have outputs, the amount of output, that's going to be your dependent variable. Here, we've chosen to think about it as crop yields. I used to be an agricultural economist. You can take the girl out of the USDA, but you can't take the USDA out of the girl. Unfortunately, I guess. I love you, USDA. I miss you, Economic Research Service. And then you have capital, the amount of machinery you have on the farm. You have labor, the amount of your children who are working on the farm. And then you have water quality, which is the environmental input. So if the water quality goes down, maybe you grow worse crops. So you do a log transformation because, remember, this is a Cobbs-Douglas production function, which means that everything's being multiplied. So we take the log of everything so that now we can run what's effectively a linear model. It's technically a log-log model, but it's effectively a linear regression. So data goes to data, and then we do Dippler mutate. We use Dippler's mutate, and then we do log of output equals log of output. Mutate allows you to perform a different transformation of the variables in your data set, log of capital, log of labor, log of water quality. And just a reminder that we're not having to use dollar signs here because we're using Dippler. We can directly manipulate the data set. We don't have to get a particular variable from the data set. And then we want to estimate a production function and summarize the results. We run a model. I think it's missing here, but we run a model where we do model goes to log underscore output plus log underscore capital plus log underscore labor plus log underscore water underscore quality. And then beta water is a coefficient of water of log water quality. And then the mean quality is the mean water quality. Mean output is the mean output. And the marginal productivity is the beta divided by the mean quality. So that's the value of the additional unit of environmental impact. And that's how you can estimate a production function. You just run a simple linear regression of the logs of output and the logs of your inputs. And with that, we're going to leave it there. For next time, we're going to finish this up with some basic time series forecasting. Thank you, and I hope you have a great day.